Chapter 19, Factors Affecting Performance. All right, so let's look at the figure here from the book. We have a bunch of different aspects and how it affects performance, and all of these are going to affect it in one way or another, either increasing or decreasing. So let's look at the top here. We'll start with diet. We've seen with body composition with diet that the amount of carbohydrates that are in your diet can greatly affect your performance, depending on what the activity is, how long it is, the intensity, as well as the intake of water and how well you are replenishing the water that is being lost during exercise. Also, we'll see a little bit in this chapter with the central nervous system functioning and arousal, as well as motivation, some psychological aspects of performance. And that could even be a whole nother course to get into with the psychological effects that it has on performance. Now, the strength and the skill that you have, that relates to how much practice, coaching possibly, as well as genetics and just natural endowment, body type, muscle fiber type, aerobic conditioning of your parents and what their top ceiling of VO2 max is. And that's going to play a large role of how aerobically fit you can be, as well as even on the anaerobic side of things as well. If you have two parents that are bodybuilders, more than likely you could have the ability to be a well-conditioned bodybuilder or power lifter or a sprinter. But if you have two parents that are more anaerobically trained, and that's the way that they're best fit for, that's the way their genetic makeup is, you might not necessarily be the best long distance runner. All right, so genetics plays a huge role in determining what your ceiling, what your upper echelon of performance could possibly be. Now, the environment also plays a role, and we've seen that in the environmental chapter. The altitude is going to play a very large role in aerobic performance, as well as the heat and humidity playing a large role in that. And that also plays into the diet and a water intake and replenishing the sweat that you're losing during exercise and heat and humidity. Now, also we have energy production from anaerobic sources, the phosphocreatine, as well as glycolysis, and that also kind of relates to carbohydrate intake with a diet, as well as the stored carbohydrates that we have in our bodies. And aerobic sources. VO2 max is going to be a good, decent predictor of performance, as well as how well you're able to buffer out lactic acid and hydrogen ions and keep the acidity from getting too low. Also, the cardiac output. From training, you can increase the cardiac output, as well as the oxygen delivery, and HB being the hemoglobin concentration, as well as the partial pressure of oxygen, getting in more oxygen to the body and being able to pump it out to the working muscles at a better pace and more efficiently use them by extracting more oxygen. And that is due to the increase in the mitochondria. With those mitochondria, you have the increase in enzymes that are used for aerobic metabolism and oxidative phosphorylation, which translates into increasing performance. So all these factors play a role in performance in one way or another. All right, so let's this next section, we're going to look at fatigue. Fatigue is a very, very general concept. When somebody says they are fatigued, you really don't know what they're talking about. You might feel tired. You might feel drowsy. You might just be wore out. But it's really vague. It's not very specific at all. So we're going to go into some of the specifics of sites of fatigue. One of them being, let's get into the definition first. So fatigue being the inability to maintain power or force of repetitive muscular contractions. One of the theories is central fatigue theory. and that the central nervous system is the place where the fatigue is going to start. And that's going to be the main cause of the fatigue. And then you also have peripheral fatigue, which are going to be neural factors. And again, in the periphery, mechanical factors within the muscles, as well as energetics of contraction deep within the muscles. So affecting the muscular contractions. And you can see the role that the brain and the central nervous system, the spinal cord plays a role. So up here would be the central fatigue portion of this, and then we got peripheral fatigue down here. Now you can see my picture down there. I'll get to that in just 1 second. So let's focus on central fatigue here. For motor unit recruitment, there's going to be a reduction in activation and firing sequence. And the theory is that this doesn't necessarily have to do with anything really neural per se, or anything going on at the muscles. It all is going to be starting at the brain. And that you have maybe a lack of motivation or some type of diversion, physical or mental diversion, that is causing some fatigue within the muscles and not being able to exert as much muscular endurance or force or power as you once were. Now, the physical or mental diversion can actually work in the opposite way, so delaying fatigue. In fact, the book describes, the authors describe situations where people were given a task while they were exercising, and they actually found out that they increased performance from this. So there was a diversion where you weren't really thinking about the exercise, you weren't really thinking about increasing the force of contraction, and you were thinking about something else, and they actually increased performance. So it could possibly be a delay in fatigue then. Also, things like shouting at yourself, self-talk type of stuff, or somebody shouting in your face, almost like a football player and the coach is getting in their face. That can actually help to increase force of contraction. That's why if someone's maxing out on a bench press, you may have some people standing around them, cheering them on. There's been a lot of studies showing that does help to increase the force of contraction and get someone pumped up. Is that really a physical? Is that mostly caused by some type of physical increase in force of contraction being the main cause, the main generator, or is it starting at the brain and working its way down to the muscles to help increase force of contraction? That would be the central fatigue theory. And the central governor model down here at the bottom. And you can see, if you are a fan of The Walking Dead like I am, I always have to put a picture in somewhere. So there's the governor standing there as he was burning down some buildings. So anyway, we get into this concept of overtraining. It can affect performance, obviously fatigue rates, stress, and circadian rhythm. Circadian rhythm is your sleep-wake cycle. Humans are basically on a 24-hour sleep-wake cycle. We have increases and decreases of arousal, and overtraining can affect that, either sleep loss or maybe sleeping too much or just being drowsy all day. It has to do with serotonin and dopamine levels. So decreasing them can help to delay fatigue, right? So decreasing the secretion of serotonin and dopamine can help delay the fatigue process, but increasing them in times of possibly overtraining or stillness or being burnt out of an activity, it can actually increase or hasten the fatigue that is going to be causing the decrease in performance. All right, going into peripheral fatigue, looking at the neural factors. So starting at the neuromuscular junction, this isn't necessarily the site of fatigue because we do know that the action potential still reaches the synapse. So there's probably not much of a fatigue happening at the neuromuscular junction site. Now, there could be some issues with neural issues where maybe that the neuron gets cut off somehow from the muscle fiber, but that's more of an injury type of factor playing along there. But just in fatigue, that's not really going to be the site. Now, if we look down deeper into the muscle and the sarcolemma and also the transverse tubules, we have the sodium-potassium pump working to help with the action potential moving down through into the muscle, so we can release calcium then and bind to troponin and go through cross-bridging and muscular contraction, move myosin and actin across each other. So with this, there's going to be a depolarization, which is going to decrease the amplitude of the action potential. If you refer to, and we didn't go over this chapter, but if you refer to the nervous system chapter, it'll talk about a threshold. The action potential is going to need to get to a certain threshold. There's always going to be some type of stimulus happening, and it needs to get to a certain threshold. And if it's starting off at a lower point, it's going to be tougher to reach that threshold, right, to become a true action potential. So therefore, if we don't have the action potentials, we're not going to have muscular contraction. Training can help improve the sodium-potassium pump function, which is one of the adaptations to training. And there's also going to be a decreased acetylcholine and release, and that's going to cause some problems with the action potential moving forward. So therefore, the action potential can be blocked in the T-tubules, and the calcium then is not going to be able to be released from the sarcoplasmic reticulum, so they combine to troponin and cause cross-bridging then, or start the flow of cross-bridging. So the reduction in amplitude may actually be a protective mechanism, however. So this can actually tend to maybe delay fatigue instead of causing it. And what's actually happening is that it can help protect the cell from further damage. So it's a protective mechanism to keep the cell in a good structure, the structural support of the cell. And ATP is needed for that. So if we're using up all of our ATP, we're not able to keep the cell healthy, essentially. So it's just helping to maintain the integrity of the cell instead of using some of that ATP for mechanical work. And we could be delaying the fatigue slightly because we're not necessarily completely blocking off all of it. And we're also, if the cell breaks down, then we are going to have complete fatigue. So, and again, it's a protective mechanism for further damage of the cell. All right, looking at pH values, and again, we're going to be going through anaerobic glycolysis, and with anaerobic glycolysis, we're going to be producing lactate, and along with that lactate, we're going to have hydrogen ions, and those hydrogen ions is what's going to be important in this concept because that's what causes the decrease in the pH within the blood. And that's going to, at some point, we're going to get to a point where we're not able to buffer it out quick enough, and we're going to start to decrease the pH. So anything less than 6.9 pH, all right, being more acidic, this is going to inhibit phosphofructokinase, or PFK. This is the rate-limiting enzyme in anaerobic glycolysis. And anything equal to or less than 6.4 is going to stop further glycogenolysis. So breaking down glycogen. We're not going to be able to break down the glycogen. And at that point, we're not going to be able to go through anaerobic glycolysis also because we can't go, because PFK now is inhibited. This can displace calcium within the muscle as well. So the hydrogen actually interferes with the binding of calcium to troponin. Again, calcium is needed to bind to troponin so it can move troponin and tropomyosin out of the way to reveal the binding site on actin, and the myosin head can attach, and we can have cross-bridging occurring and having myosin pulling actin towards the M line. So if we don't have that cross-bridging, we're not going to have a force of contraction that is necessary for that activity. And for short duration, high intensity activity, this is going to be the primary cause. We're talking 10 seconds to about 3 minutes in length. This is going to be the main cause of the fatigue and the decrease in performance. So again, the cross bridging is what's affected here. Also, we could have an accumulation of inorganic phosphate. Keep in mind, when we're mechanically moving the muscles, we are stripping away one inorganic phosphate from ATP so that we can transfer that energy to a different form. All right, so we can have mechanical work. And some of it's going to be lost as heat as well. Some of that energy is going to be lost as heat. But we have some accumulation of inorganic phosphate at times. And this can inhibit maximal force production because it reduces cross-bridge forming. And sometimes we might not have the ADP necessary to be able to add back onto the inorganic phosphate. We might not have the phosphocreatine necessary as well. So the calcium release is also inhibited, again, causing problems with cross-bridging of myosin and actin. And the same thing as before, the ATP utilization is slowed down. And this helps to maintain the ATP concentration. Again, it's needed for protection against further cell damage. Now, looking at the muscle fiber types, the fibers that are recruited first, and they're more often going to be recruited, those are the ones that are going to fatigue a little bit quicker. And also, recruitment order and intensity is going to play a big role in this too. If you look at over here in the figure, the exercise intensity, and this is in percentage of VO2 max, and the active muscle fibers, so the percentage of the active muscle fibers, as we go up in exercise intensity, we are starting to recruit the muscle fibers that are able to generate higher amounts of force. Now, these are going to not be fatigue resistant. Again, the type 1 fibers are more fatigue resistant. But if you're only exercising at 40 or 50% VO2 max, these are going to be the fibers that are going to fatigue first because you're not really using the type 2A or type 2X all that often. Now, if you're in a higher intensity activity, the type 2 muscles are going to be fatiguing quicker than the type 1 fibers because you're using them more than the type 1 fibers during that specific activity. All right, looking at ultra short-term activity and the factors that are limiting anaerobic performance. Now, ultra short-term activity are things like jumps, very quick explosive movements, basically less than 10 seconds. It could be short sprints, maybe shuttle runs. These are going to rely heavily on type 2 muscle fibers. And also motivation, skill, and practice are going to go into these. There could be certain forms that are necessary to limit the amount of wasted movement and wasted energy that is used during these activities. And again, the energy system is going to be the ATP, PCR, as well as anaerobic glycolysis as well. So if we look down here in the figure, we have practice. Talking about practice, man. So practice is going to play into the skill and the technique that you possess. And that's obviously going to affect the performance in this activity. Again, less than 10 seconds. On the other side, we have motivation and arousal. How motivated you are, how aroused you are to partake in this activity. And that's also going to play into the fiber type distribution and also the recruitment pattern that is developed. Again, the energy system is going to be the ATP PCR system as well as glycolysis, anaerobic glycolysis in this case. And that's all this is going to relate to muscular power and how much power you can generate within the muscles. And both sides of these are going to combine and give you the performance for that ultra short-term exercise. Going a little bit further with short-term exercise. So we're talking 10 seconds to about 3 minutes in length. Now, this is going to vary a little bit in terms of what system you're using to produce most of the ATP. At the low end, in terms of time, you're looking at more anaerobic systems. So the ATP PCR as well as anaerobic glycolysis. You're really starting to get into the anaerobic glycolysis with this activity, this short-term activity. Towards the end, once we get into 3 minutes, that you're really going to start to produce a lot of ATP through aerobic metabolism and oxidative phosphorylation. Now, because the body has got to that point where it has got enough oxygen available to reach a steady state for that type of exercise. Generally speaking, 3 to 4 minutes is where you're going to reach that steady state where the oxygen demand has now reached, or the oxygen that you're bringing in has now reached the oxygen demand for that activity. Now, being that anaerobic glycolysis is actually going to play a big role throughout most of this time period, there's going to be hydrogen that's going to be accumulating, and that's going to increase the acidity level or decrease the pH. And having buffers to buff that out, to buffer that out and to help to alleviate some of that acidity is going to be helpful. And through proper training, you can develop systems to buffer the all that out and try to delay fatigue a little bit further. Now, again, the fiber type distribution and recruitment is going to play a major role in this. And the type 2 muscle fibers mostly going to be the anaerobic metabolism, and the type 1 muscle fibers mostly going to be the aerobic metabolism. And that's going to be mostly towards the end. All right, the VO2 going to be important. The type 1 muscle fibers really important towards the end of that activity, because that's where we're going to start to get into aerobic metabolism. At the start and even halfway through, there's going to be up to about that transition point, probably around 2.5 minutes. You're going to start to transition from anaerobic to aerobic metabolism. Now, it's not an on and off switch. It's just that you're going to switch from the anaerobic system producing much of the ATP to the aerobic system producing most of the ATP. Now, again, the glycolysis is also going to increase increase the acidity level and the hydrogen level within the blood. And again, the buffer systems are going to help to try to alleviate that. And this is where the fatigue is going to be setting in during this type of activity. Let's go to moderate length exercise. So 3 to 20 minutes. Most of this is going to be aerobic metabolism. So the cardiovascular system is going to play a major role in determining the health of the cardiovascular system and the level of training that it has. So the stroke volume, hemoglobin content, mitochondria, and with the mitochondria, that AVO2 difference, that arterial venous difference of oxygen, how well you're able to extract that oxygen and utilize it once you get down into the muscles. Also, the muscle fiber types are going to play a big role in the aerobic performance 3 to 20 minutes. So the type 2 muscle fibers, they're going to be recruited, but they're just not recruited in high amounts. But we are still going to have them recruited. So we're going to have some hydrogen ion production and lactate production. So that could be a cause of fatigue during this activity. So if we look at the figure, we have genetics and training. Again, I mentioned that genetics plays a huge role in determining your upper echelon or your ceiling of where you can get to. And training is going to be very key to this as well. And that helps to determine the stroke volume max and the heart rate max. And we know from previous lectures that heart rate times stroke volume is equal to cardiac output. So if you take the max of both of those, heart rate max times stroke volume max, that will equal cardiac output max. And the cardiac output is one of the components of the equation of VO2. Now, on the other side, we have, again, training can help increase mitochondrial content as well as oxidative enzymes. also, we start to build more capillaries, more venues for more pathways for the blood to travel through. And it also helps to increase cross-sectional area for gas exchange once we get down into the muscles. And again, genetics playing a role in the fiber type, as well as the mitochondrial and capillary density, and how developed the muscles are to those increases in oxygen supply, as well as handling the oxygen. And with that, we have hemoglobin concentration, and we have inspired oxygen. This FiO2 is known as fractional inspired oxygen, just the percentage of oxygen that you inspire that is oxygen, or percentage of air that you inspire that is oxygen. We have hemoglobin concentration and the partial pressure of oxygen. So once we get into this type of activity, this 3 to 20 minutes, if you're in a high altitude environment, it could start to affect you during these types of events. So the PO2 can affect this, and this is just arterial oxygen. All right, and the CVO2 is venous oxygen. All right, the authors, some authors refer to it as CaO2 or CVO2. I usually refer to it as AO2 or VO2. All right, so V as a lowercase v being the veins, and then A being the arteries. So just how much oxygen is in the arteries versus the veins. And this dash here, this subtraction point, is how much oxygen is extracted once the blood passes past the muscles then. And if we remember the Fick equation, VO2 max, or VO2 is equal to cardiac output times a VO2 difference, times this over here. So again, the VO2 max being the key component here and playing into the aerobic performance for this moderate length activity. Let's go to intermediate length. So we're getting up to about an hour now. And again, predominantly aerobic. It doesn't mean that anaerobic systems are not providing any ATP. They are still providing some ATP, just not a whole lot of it. Not nearly as much as what the aerobic system is providing. So having a high VO2 max and running economy, having proper form, not having a lot of wasted movement, good biomechanics, as well as the bioenergetics, and that plays into the type of training that you have. Lactate threshold also starts to play a major role once we get into intermediate length. Really, once we get closer and closer to that 1 hour mark. So again, looking at the figure, how this flows and how everything affects the aerobic performance in this intermediate length. So we have a heat load or dehydration playing major factors in how dehydrated someone could be in the cardiovascular drift. And we've seen that in the last couple chapters, and how that affects VO2 max and even rating of perceived exertion. That could even play a little bit into the psychological aspect of this as well. So that VO2 max then goes into steady state VO2. And that steady state VO2, basically you're trying to get to the highest point of the percentage of your VO2 and try to maintain that throughout the entire exercise. Now, lactate threshold is going to be the major factor in determining that percentage of VO2 max that you can exercise at without fatiguing very quickly. All right, that lactate threshold is the point where your body has an inability to buffer out the lactate, and it's they're going to have this very large and significant increase in lactate, and because the body is just not able to deal with that much concentration of it. So if we look, we also have on the other side biomechanics, and we talked about that up here, the running economy and bioenergetics. And the type 1 fibers, percentage of type 1 fibers can play a big role in that, and at least the bioenergetics, some in the biomechanics, and how well those type 1 fibers are trained for the activity. But also the percentage of type 1 fibers could play a role in the lactate threshold, being that the type 1 fibers are more aerobic, and the type 2 fibers that are, if you have more type 1 fibers, you could possibly have a better lactate threshold, maybe. Just how well the training is that you're going through. So again, all this causing an effect on aerobic performance, again, from about 20 minutes to 60 minutes. And let's look at long-term exercise. Now we're getting into really long, slow distance exercises. So there a very minimal amount of ATP being generated through the anaerobic systems. Environmental factors start to play a bigger and bigger role once we get past 1 hour. Because as we've seen with the environment, the hotter it is, the more humid it is, that's going to affect the amount of water that we're losing through sweat, as well as electrolytes. So it's important to get enough fluids and electrolytes and replenish that throughout this, throughout the duration of this activity. Also, once we get to altitude, what altitude are you exercising at? If it's at sea level or 500 feet above sea level, not really going to make that big of a deal, or even 1,500 feet, probably not going to make that big of a deal. But once you start getting to 8, 10, 12, 14,000 feet, you're going to start to have some problems and start to have a decrease in arterial saturation, which is going to translate into less oxygen being supplied to the muscles. So that's going to decrease the VO2 max and decrease your aerobic capacity, decrease your performance and your exercise intensity then. Also, the rate of carbohydrate utilization and how well you were, or how plenished you were in carbohydrates or glycogen at the start of the exercise, and how depleted are you becoming throughout that exercise, and are you ingesting any more carbohydrates to help to maintain the blood glucose and to help keep you going through that activity, push you past the 2, 3, 4 hour mark. So looking at the figure down here, and I'm going to blow this up real quick so you can see it just a little bit better. There we go. I'm going to hide some of the text there, but anyway, we have the supplement during exercise. That would be carbohydrate ingestion. And again, diet is going to play a big role in that, and how well you had stored the glycogen in the liver and the muscles, and playing a role into the percentage of VO2 max, in dehydration and heat load, the environment playing a key role. And again, the same thing with the intermediate length. We have the biomechanics as well as the bioenergetics and running economy playing a role on the other side. And the type 1 fibers, the percentage of type 1 fibers is going to tend to dictate that. And also that's going to help to dictate the lactate threshold as well. Again, playing into VO2 max and steady state VO2 max, trying to get up to the highest percentages possible without causing the lactate to accumulate to the point where the fatigue sets in very quickly and you have to stop the exercise. So again, the aerobic performance at 1 to 4 hours. Okay, that was chapter 19, factors affecting performance. If you have any questions, you can leave a question in the comments below, or you can email me. I thank you for watching.